Welcome to Unit 2, where we will be focusing on combinational MOS logic circuits. This section will cover the essential concepts and design principles behind combinational circuits using MOS technology. I'm Arul Albert, and I'll be guiding you through this material. Let's dive into understanding how these circuits work and their applications. On this slide, we outline the syllabus for our course. We'll begin by exploring various circuit families, starting with static CMOS, which is the foundation for many digital circuits due to its robustness and low static power consumption. Then, we'll move on to ratioed circuits and cascode configurations, which offer different trade-offs in speed and power. We'll also cover advanced logic styles like voltage switch logic and dynamic circuits, which use clocking and pre-charge techniques to improve performance. Pass transistor logic and transmission gates will be discussed as alternatives that can reduce transistor count and power usage. Additionally, we'll dive into domino logic and its variations, including dual-rail domino and complementary pass transistor logic, which are popular in high-speed designs. Other specialized styles like DCV-SPG and DPL will also be reviewed, along with common pitfalls to watch out for when designing these circuits. Finally, we'll focus on power considerations, exploring dynamic power that results from switching activities, static power due to leakage currents, and strategies for low-power architecture design. Understanding these topics is crucial for creating efficient and reliable integrated circuits. Here we have a comparison between combinational and sequential logic circuits. Starting with combinational logic, the output depends solely on the current inputs. In other words, the output is a function of the input at that exact moment, with no memory of past inputs. This means if you change the input, the output immediately changes accordingly. On the other hand, sequential logic circuits have outputs that depend not only on the current inputs, but also on previous inputs or states. This introduces the concept of memory in the circuit, where the output is influenced by both the current input and the past history of inputs. This is essential for designing systems like counters, registers, and memory devices that need to remember past information to operate correctly. So, the key difference is that combinational logic is stateless and purely input-driven, while sequential logic is stateful, relying on input history, which enables more complex behaviors. Digital logic can be broadly categorized into two main types: combinational circuits and sequential circuits. Combinational circuits are straightforward. Their outputs depend solely on the current inputs at any given moment. There's no memory involved here, so they respond instantly to changes in input. On the other hand, sequential circuits are a bit more complex because they possess memory. This means their outputs depend not just on current inputs, but also on past inputs or states. This memory allows them to store information and create more dynamic behavior. When it comes to building these circuits, the primary components differ. Combinational circuits are constructed using logic gates like AND, OR, and NOT gates. Meanwhile, sequential circuits rely on elements like registers and latches, which help maintain the memory aspect. Understanding this fundamental distinction is key to grasping how digital systems function. Now let's dive into static CMOS logic, which is fundamental in digital circuit design. We'll start with an introduction to the concept, emphasizing how complementary CMOS works by using both P-type and N-type transistors to achieve efficient switching. Then we'll explore bubble pushing, a technique used to simplify logic expressions by moving inversions around. Next, I'll explain compound gates, which combine multiple logic functions into a single gate to optimize performance. We'll also look at skewed gates, designed to favor one input transition over another, and asymmetric gates, where transistor sizes are adjusted to balance delay and power. Finally, we'll discuss the P/N ratio, the sizing relationship between P-type and N-type transistors, which is crucial for ensuring proper drive strength and switching characteristics in CMOS circuits. Understanding these concepts is key to mastering the design of efficient and reliable digital logic circuits. Let's talk about static CMOS gates. They are made up of two main parts: the pull-up network, or PUN, and the pull-down network, known as PDN. In static CMOS, The output of the gate is always connected to either the supply voltage VDD or ground VSS through a low resistance path. This means the output reliably represents the Boolean function of the circuit at all times, except during switching transitions. On the other hand, dynamic CMOS works differently. Here, the output depends on temporarily stored signal values held by the capacitance at nodes with high impedance. Dynamic CMOS circuits use a clock signal to control the operation, which makes it a unique design method in integrated circuit design for implementing combinational logic. This distinction between static and dynamic CMOS is crucial when choosing the right approach for a specific application. Here we're reviewing the concept of static CMOS, which relies on two complementary networks, the pull-up network, or PUN, and the pull-down network, or PDN. The PUN is made up exclusively of PMOS transistors, while the PDN consists only of NMOS transistors. This complementary arrangement ensures that the output node is either connected to the supply voltage VDD through the PUN or to ground, labeled VSS, through the PDN, but never both at the same time. This dual network structure is fundamental for creating efficient and low-powered digital logic circuits. Inputs, such as in 1, in 2, and in 3, control these networks to produce the desired output function, indicated here as F equals G. Understanding the balance and interaction between the PUN and PDN is key to mastering CMOS circuit design. Here, we're focusing on the fundamental structure of static CMOS logic. It consists of two main networks, the pull-up network, or PUN, and the pull-down network, or PDN. These work together to implement the desired logic function. The pull-up network is responsible for connecting the output to the positive supply voltage when the output should be high. Conversely, the pull-down network connects the output to ground when the output should be low. Understanding these two complementary networks is essential because they form the basis of the reliable and efficient operation of static CMOS circuits. Now, let's talk about bubble pushing. This technique is used to represent the Boolean functions of and OR gates by using NAND and NOR gates instead. The key to this conversion lies in De Morgan's law. Essentially, a NAND gate can be thought of as an OR gate with all inputs inverted before being ORed together. Similarly, a NOR gate acts like an AND gate, but again with all inputs inverted. This principle not only applies to simple two-input gates, but also extends to gates with multiple inputs. Understanding this relationship allows us to transform complex logic expressions into simpler forms using NAND and NOR gates, which are often more practical to implement in digital circuits. Here, we're looking at how to use De Morgan's law to push negations or bubbles through logical expressions. This technique is really useful because it helps simplify complex logic by transforming negations in a way that can make the expression easier to analyze or implement. Essentially, De Morgan's law tells us how to switch between ANDs and ORs when we're dealing with negations, converting something like the negation of a conjunction into a disjunction of negations, and vice versa. This means we can push the bubble, or the not operator, deeper into the expression, breaking it down step by step. Understanding this process is key because it forms the basis for many simplifications and transformations in logic circuits and Boolean algebra. Here we're focusing on the technique called bubble pushing. It all starts with a network made up of and OR gates. The first step is to convert this network into one that uses only NAND or NOR gates along with inverters. Once that's done, we can push the bubbles, those inversion symbols, through the circuit. This process helps us simplify the logic by applying De Morgan's law, which is crucial to understand here. Essentially, this law shows how inverting inputs and outputs can transform and gates into or gates and vice versa, allowing for cleaner, more optimized designs. The key takeaway is that by systematically moving these bubbles and using the right gate conversions, we can achieve simpler, more efficient logic circuits. Now, let's talk about compound gates in static CMOS technology. One of the key advantages here is efficiency. Static CMOS handles compound gates more effectively compared to basic logic gate implementations. Essentially, compound gates allow us to compute multiple functions within a single stage, like combining and/or and invert operations together. This integration reduces the overall delay because the signal doesn't have to pass through several separate gates. By using compound gates, we achieve faster performance and more streamlined circuit designs, which is crucial for optimizing speed and power consumption in modern electronics. Now let's dive into the concept of logical effort as it applies to compound gates. Logical effort is a way to measure how much a gate slows down a signal compared to a simple inverter. When we talk about compound gates, which are made up of multiple transistors arranged in more complex ways than a single gate, their logical effort reflects how their structure impacts signal delay. Understanding this helps us optimize circuit speed because it guides us in choosing or designing gates that minimize delay. Essentially, by analyzing the logical effort of compound gates, we can predict their performance and make more informed decisions in our circuit design process. It looks like this slide is currently empty, so there's nothing specific to go over here. If you have any points or topics you'd like me to cover for this slide, just let me know. Here, we are focusing on the estimation of logical effort, which is a key concept in evaluating the delay introduced by different types of logic gates. Logical effort is essentially a way to quantify how much slower a gate is compared to an inverter, which is taken as the baseline with a logical effort of 1. Starting with the inverter, its logical effort is always 1, regardless of the number of inputs, because it's the reference point. For NAND and NOR gates, the logical effort depends on the number of inputs. For example, a 2-input NAND gate has a logical effort of 4/3, while a 3-input NAND gate is 5/3, and this grows linearly as the number of inputs increases. Similarly, 2-input NOR gates have a logical effort of 5/3, 3-input NORs have 7/3, and this also increases with the number of inputs. The table here summarizes these values clearly, showing how the logical effort for NAND and NOR gates can be calculated based on the formula that includes the number of inputs. This helps us estimate the delay more accurately when designing circuits by assessing the relative performance of different gate configurations compared to a simple inverter. Understanding this allows us to optimize our circuits by selecting gates that provide the best trade-off between functionality and speed, ensuring efficient overall design. Here, we're looking at the concept of skew in digital circuit design. Skew happens when the same signal reaches different parts of a design at slightly different times or phases. This can affect how the circuit behaves and how quickly it responds. To manage this, we use what's called skewed gates. There are 2 types: HI skew gates, which are designed to favor the rising output transition, meaning they help the signal go from low to high more quickly. Then there are LO skew gates, which favor the falling output transition, helping the signal change from high to low faster. One way to achieve this favoring is by decreasing the size of the non-critical transistor within the gate. This tuning changes how the gate responds during the rising or falling transitions. Furthermore, we describe the logical effort for these transitions separately. GU refers to the logical effort for the rising or upward transition, while GED is for the falling or downward transition. Both are calculated as the ratio of the input capacitance of the skewed gate to that of a standard, unskewed inverter with the same drive strength for the given transition. Understanding and applying skew adjustments like this helps in optimizing signal timing and improving overall circuit performance. Here, we're looking at skewed gates, which essentially favor one edge of the signal transition over the other. For example, if the rising output of an inverter is the most critical for your circuit's timing, you might choose to downsize the non-critical NMOS transistor to optimize for that rising edge. This process involves calculating the logical effort by comparing your skewed gate to an unskewed inverter that has the same effective resistance on the critical edge. We denote GU as the logical effort for the unskewed inverter with equal rise resistance and GED for the one with equal fall resistance. This allows us to understand how the skew affects the gate's performance in terms of delay and drive capability. Essentially, skewing lets you tailor the transistor sizes within the gate to improve timing for the most important transition at the expense of less critical edges. This is especially useful in high-performance designs where every fraction of delay counts. Skewed gates are designed to favor one edge of the signal transition over the other. For example, if the rising output of an inverter is the most critical path in your circuit, you can optimize by downsizing the non-critical NMOS transistor. This adjustment helps improve performance where it matters most. To quantify this, we calculate the logical effort by comparing the skewed gate to an unskewed inverter that has the same effective resistance on that specific edge. In this case, the logical effort for the rising edge, GU, is found by dividing 2.5 by 3, which simplifies to 5/6. For the falling edge, GD, it's 2.5 divided by 1.5, giving us 5/3. This means the gate is deliberately unbalanced or skewed, with different logical efforts for rising and falling transitions. This skew can help optimize overall circuit timing by prioritizing the critical signal edges while potentially sacrificing the non-critical ones. Essentially, we tailor the transistor sizes to achieve the best performance where it counts most. Here, we're looking at the concept of HI and LO skew in logical effort. Simply put, the logical effort of a skewed gate for a specific transition is the ratio between its input capacitance and the input capacitance of a standard inverter that provides the same output current for that transition. Skewed gates help by reducing the size of the non-critical transistors, making the design more efficient. When we talk about HI skew gates, they are optimized to favor a rising output, which means a smaller NMOS transistor is used. On the other hand, LO skew gates favor a falling output, so they have a smaller PMOS transistor. This skewing affects the logical effort. It's reduced for the favored transition direction, improving performance there, but it actually increases for the opposite transition. This trade-off is key to understanding how gate sizing and skewing impact timing in circuit design. It looks like this slide is currently blank. If there's specific information or key points you'd like me to cover here, please let me know so I can help craft the narration accordingly. It seems that the slide does not contain any visible content or text to discuss. Could you please provide more information or clarify the content you'd like me to narrate? It seems this slide doesn't contain any visible content or specific information to discuss. If there's a particular topic or section you want me to focus on, please let me know so I can provide a detailed explanation. Otherwise, we can move on to the next slide where there's clear content to review. It looks like this slide is currently blank or missing content. Could you please provide the text or main points that are supposed to be on this slide? That way, I can help you craft a clear and engaging narration. It seems this slide is blank or contains no visible content. If there's supposed to be information here, please let me know so I can help you craft the narration. Otherwise, I'm ready to assist with the next slide. Here we're looking at symmetric gates, which are designed so that their inputs can be perfectly symmetric. This means that the behavior of the gate remains consistent no matter how the inputs are arranged. For example, if you swap inputs A and B, the output stays the same. This symmetry is important in circuit design because it ensures predictable and reliable operation. The numbers you see here illustrate how the inputs relate to the output in a balanced way, reinforcing the concept that the gate treats inputs equivalently. Understanding symmetric gates helps us design more robust and efficient digital systems. Here we're looking at the concept of asymmetric skew in digital circuits. The main idea is to combine asymmetric and skewed gates to optimize performance. By downsizing the non-critical transistors connected to less important inputs, we effectively reduce parasitic delay on the critical input path. This means the signal that matters most can pass through faster, improving overall timing. You'll notice that the transistor sizing numbers like 4, 2, and 1 indicate how we scale the transistor widths, assigning larger sizes to critical paths and smaller ones to non-critical signals. This selective sizing achieves better speed without unnecessary power or area costs. The reset and output labels here illustrate how this approach is applied in practical circuit designs, balancing timing needs with efficient transistor use. It looks like this slide doesn't have any content on it. If you intended to include key points or information here, please provide that so I can help craft the narration for you. It looks like this slide is currently empty or doesn't contain any visible content. If this is intentional, I can help you by suggesting what to include here or how to present this part of the presentation effectively. Could you please provide more details or confirm if there's specific content you want to discuss on this slide? I notice that this slide doesn't have any specific content displayed. Could you please provide the text or key points that should be covered on this slide so I can create a detailed narration script for you? Now let's take a closer look at ratioed logic, starting with the introduction to pseudo-NMOS logic gates. Pseudo-NMOS is a type of logic design that combines a pull-up transistor, usually a p-type, that is always on, with pull-down NMOS transistors that are controlled by the inputs. This setup creates what's known as a ratioed logic gate, because the output voltage depends on the ratio of the strength of the pull-up transistor to the pull-down transistors. Essentially, the pull-up transistor weakly pulls the output high, while the pull-down transistors strongly pull it low when they are activated. This design is notable for its simplicity and speed, but it also comes with trade-offs like static power consumption, since the pull-up transistor is always conducting current. Understanding these basics sets the stage for diving deeper into how pseudo-NMOS gates function and their applications. Here, we're looking at ratioed logic circuits, which are designed to reduce the number of transistors needed in a circuit. The key idea is that instead of using a full pull-up network, or PUN, we replace it with a single unconditional load device. This device actively pulls the output up whenever the pull-down network, or PDN, is turned off. This approach simplifies the design and can save space and power, but it also has trade-offs in terms of speed and noise margins that we'll discuss later. The important thing to remember is that ratioed logic relies on this single load device to manage the output rather than a complex network of transistors. Here we're looking at ratioed logic circuits, which are a key concept in digital design. The main goal here is to reduce the number of devices compared to traditional complementary CMOS technology. This means using fewer transistors, which can save space and potentially power, but it requires careful design to make sure the circuit functions reliably. In ratioed logic, the output depends on the relative strength or ratio of different transistors, rather than having fully complementary pull-up and pull-down networks. For example, you might see a resistive load or a depletion mode load used in place of a PMOS pull-up transistor. These loads help to simplify the circuit but introduce constraints. There are three main variations shown: resistive load, depletion load NMOS, and pseudo-NMOS logic. Each has its characteristics. Resistive loads are simple but can waste power. Depletion loads use a transistor operating in a specific mode to provide a more efficient load. Pseudo-NMOS uses an always-on PMOS transistor to pull the output high, which enables faster switching, but must be carefully balanced with a pull-down network. The critical point is the design balance. Since these circuits rely on transistor ratios, any variation in manufacturing or operating conditions can affect performance and correctness. That's why careful design and sizing of transistors is essential to ensure that outputs switch correctly and noise margins are acceptable. Overall, ratioed logic offers benefits in transistor count and layout simplicity, but demands careful engineering to maintain reliable operation. Here we have an overview of ratioed logic, which is a key concept in circuit design. The basic idea involves using a resistive load, denoted as RL, in combination with a pull-down network, or PDN, which is controlled by the input signals in 1, in 2, and in 3. The circuit is powered by V2D, and the ground reference is VSS. An important point to remember is that the output voltage VOH is ideally equal to VDD when the output is high. The output voltage at low level, VOL, depends on the ratio of RL to RPDN, the resistance of the pull-down network. To maintain a good noise margin, the load resistor RL must be much larger than RPDN, which keeps VOL low enough to be recognized as a logic 0. The delay time, specifically TPLH, or the propagation delay from low to high, is influenced by RL and the load capacitance CL. According to the equation, TPLH equals 0.69 times RL times CL. Despite its simplicity, ratioed logic faces challenges. First, there is static power dissipation because the resistor continuously draws current when the output is low. Second, implementing a large resistor, say 40 kiloohms, physically requires a substantial area on the chip, roughly equivalent to 3,200 square micrometers of end diffusion, which translates to about 1,000 transistors. This makes it impractical in many integrated circuit designs. Understanding these trade-offs is crucial when deciding whether ratioed logic fits a particular application. It highlights the balance between simplicity, power consumption, and silicon area efficiency. Here, we're looking at different types of active loads and how they operate within a circuit. First, we have the depletion load, which uses a depletion mode transistor. This transistor is unique because it has a negative threshold voltage, meaning it turns on even when the gate-to-source voltage is zero. This characteristic allows it to function as a load without the need for additional biasing. However, one thing to watch out for is the body effect, which could influence the transistor's threshold voltage and potentially cause issues in the circuit. Next, there's the PMOS load, which is a common active load configuration using a PMOS transistor. This setup typically connects to the positive supply voltage, or VDD, and is used to provide a constant current load. Then, we have the pseudo-NMOS load, which uses an NMOS transistor with its gate connected to ground, effectively creating a load without requiring an external biasing voltage. This approach simplifies the design but can have certain trade-offs in terms of power consumption and performance. Understanding these different active load types helps in designing efficient and stable analog circuits, especially when considering factors like threshold voltages and the impact of body effects. Here we are looking at the pseudo-NMOS logic style. One key advantage of this approach is that it avoids issues related to body effect, which can complicate transistor behavior in other designs. When implementing an N-input gate, we only need N plus 1 transistors, which is quite efficient. Each input controls exactly one transistor, reducing the load on the previous stage compared to other logic types. However, there are some trade-offs. Pseudo-NMOS circuits consume static power when the output is low, meaning there's a continuous power draw even when the circuit isn't switching. For example, if a minimal-sized gate uses about 1 milliwatt of static power, a large circuit with 100,000 gates could consume as much as 50 watts just in static power, assuming half the gates are in the low output state. This static dissipation can be significant alongside the dynamic power. Another consideration is that these gates often have asymmetric rise and fall times, which can affect timing and performance. Because of these factors, pseudo-NMOS is mainly effective for small parts of a circuit where speed is critical, such as address decoders in memory systems. Overall, while this design has its benefits in speed and simplicity, the power trade-offs limit its broader use. Here, we're looking at pseudo-logic circuits and focusing on their static power consumption when operating in the low output mode. The equation plow equals VDD times ILO represents this power consumption. Essentially, this tells us that the static power dissipated is directly proportional to both the supply voltage and the current when the output is low. Understanding this relationship is crucial for optimizing circuit design to minimize power use in standby or inactive states. It looks like this slide is blank or does not contain any visible content to discuss. Could you please provide more details or check if the slide has any hidden notes or points you'd like me to cover? Here, we're comparing ratioed and ratioless logic styles. Ratioed logic depends on the ratio of the PMOS and NMOS transistor sizes, specifically the beta P over beta N ratio, to determine the gate's overall behavior. This means the output voltage levels rely on this size relationship. On the other hand, complementary CMOS logic is considered ratioless because the output levels don't depend on transistor sizes, making the design more stable in that sense. One downside of ratioed logic is that it tends to have slow rising transitions, which can affect performance. However, it offers several advantages. It supports large fan-in, making it suitable for gates with many inputs. It's also compact and simple in design with a low transistor count, which can lead to high-speed operation. So, while it has some trade-offs, ratioed logic can be very efficient and effective depending on the application. Cascode voltage switch logic, or CVSL, aims to combine the advantages of ratioed circuits while eliminating static power consumption. The key idea here is that CVSL uses both the true and complementary versions of the input signals. This approach allows it to produce both true and complementary outputs. The implementation involves two NMOS pull-down networks. One network, called the pull-down network F, carries out the logic function just like a traditional static CMOS gate. Meanwhile, the other network, F', takes the inverted inputs and arranges the transistors in a complementary conduction pattern. This setup helps achieve efficient switching without the static power loss you typically see in other logic styles. Here, we see how, for any given input pattern, one of the pull-down networks will be on while the other is off. This creates a low output at the pull-down node, which then activates the PMOS transistor to pull the opposite output high. As this output rises, the other PMOS transistor switches OFF, ensuring that no static power dissipation occurs. The figure illustrates a CVSL and /NAND gate, clearly showing the complementary nature of the pull-down networks. One has parallel transistors, while the other has them in series. This complementary operation is key to the circuit's efficiency and functionality. Here we have a figure showing a 4-input XOR gate. One important aspect to notice is how the pull-down networks share the transistors for inputs A and its complement, a bar. This sharing reduces the total number of transistors required by 2, which is a significant optimization. Sharing transistors like this is quite common in complex logic functions because it helps minimize the overall transistor count, saving space and power. Additionally, there are systematic design methods that allow us to identify and implement these shared networks efficiently, improving both the performance and cost-effectiveness of the circuit. Here, we highlight the main advantages and disadvantages of CVSL or current mode logic. One major advantage is its high potential speed. This speed boost comes from performing all the logic operations with NMOS transistors, which effectively reduces the input capacitance and allows for faster switching. On the downside, CVSL gates require both low-going and high-going transitions. This necessity introduces additional delay, which can impact overall performance. Additionally, during the switching period, there is a contention current, where both transistors can conduct simultaneously. This increases power consumption, making CVSL less energy efficient. Finally, it's important to note that CVSL is not well suited for implementing general NAND and NOR logic gates, limiting its flexibility in certain digital circuits. So, while CVSL offers speed advantages, these come with trade-offs in power and design complexity. Here, we're looking at differential cascade voltage switch logic, or DCVSL. This logic style uses a pair of cross-coupled inverters along with differential inputs, which helps in reducing noise and improving speed. The key advantage of DCVSL is its ability to offer full voltage swing outputs, which ensures better signal integrity compared to some other logic styles. This makes it particularly useful in high-speed and low-power digital circuits. Understanding DCVSL is crucial because it combines good noise margins with efficient switching, making it a popular choice in advanced circuit designs. Here, we're focusing on pass transistor logic. This approach uses transistors as switches to pass logic levels directly between circuit nodes, rather than relying on traditional gate structures. The key advantage is improved efficiency in terms of speed and power consumption, especially in complex logic circuits. However, it also has some challenges, such as signal degradation, so careful design is required to maintain signal integrity. Understanding pass transistor logic is crucial for optimizing performance in many modern digital systems. Here, we're discussing pass transistor logic, which is a bit different from the standard use of MOSFETs. Normally, the primary inputs are only connected to the gate terminals of MOSFETs. But in pass transistor logic, inputs can be connected to both the gate and source terminals. This approach allows more flexibility in circuit design. In the typical structure shown here, we use NMOS transistors. P1 and P2 represent the pass variables, and these should always be connected to the source terminals of the transistors. On the other hand, G1 and G2 are the gate or control variables, which connect to the gate terminals. Together, these variables enable the transistor to act as a switch that can pass signals through, leading to efficient implementation of certain logic functions. This method can reduce transistor count and improve speed in some cases compared to traditional CMOS logic. Here, we're looking at how Karnaugh maps, or K-maps, group signals that share the same properties. This grouping helps simplify the logic design. Specifically, when implementing basic gates like the AND gate using pass transistor logic, we start by creating the truth table. This truth table outlines all possible input combinations and their corresponding outputs. From there, we derive the pass function, which is essentially a mathematical way to represent how the inputs relate to the output. Understanding this pass function is crucial because it guides us in designing the circuit using pass transistors efficiently. Here, we're looking at the AND gate with a focus on its truth table and how it relates to the pass function through a Karnaugh map or K-map. The K-map we're using is a 2x2 grid where we place the variable A, called the pass variable, along the rows, and the variable B, the control variable, along the columns. This setup helps us organize how the pass function is defined. You can see that the pass function for the AND gate is expressed as and equals B times B plus B times A, showing how the inputs combine. The truth table summarizes the behavior. For inputs A and B, the output is 1 only when both A and B are 1, otherwise it's 0. This aligns with the pass function, which is a plus B, indicating that the output depends on both variables controlling the gate. Understanding this mapping provides a clear way to visualize and design logic circuits using these fundamental concepts. Here, we see how grouping variables of the same type helps us derive the Boolean expression. Specifically, for the AND function, the expression is given as BB plus BA. This expression can be implemented using pass transistor logic, which is an efficient method for realizing Boolean functions at the transistor level. By following this approach, not only the AND function, but all other logic functions can be implemented similarly, making the design process straightforward and consistent. The key takeaway is that grouping variables effectively leads to simpler Boolean expressions that can be directly implemented in hardware. Here, we have the truth table and pass function for the OR gate. The OR gate outputs a high signal, or 1, when at least one of its inputs, A or B, is high. Looking closely at the truth table, whenever A or B is 1, the output is 1. The only time the output is 0 is when both A and B are 0. The pass function for the OR gate can be expressed as AB plus BB, which simplifies the logic. This is also illustrated in the 2x2 Karnaugh map, which helps visualize how the output depends on the control variable B and input A. Essentially, the OR gate allows a signal to pass through if either A or B is active. This same approach can be extended to implement other logic gates as well, by adjusting the pass functions and control variables accordingly. Understanding this connection between truth tables, pass functions, and K-maps is key to designing and analyzing digital circuits efficiently. It looks like this slide does not contain any visible content or key points to discuss. If there's something specific you'd like me to explain, or if this is a placeholder slide meant for a break or transition, please let me know how you'd like me to proceed. It seems there's no specific content provided on this slide for me to discuss. Could you please share the text or main topics covered on this slide so I can create an appropriate narration? It looks like this slide doesn't have any content to discuss. If you have any specific topics or points you'd like me to cover, please let me know. It seems like this slide is blank or doesn't contain any specific content for us to discuss. If you have any particular points or topics you'd like me to cover here, please let me know so I can provide a detailed explanation. Otherwise, we can move on to the next slide that contains key information. It looks like this slide is blank or contains no visible content. Without specific information or text to guide us, there's nothing to explain here. If this is an intentional break or placeholder, we can use this moment to recap what we've covered so far or prepare for the next topic. Please let me know if there's any particular focus you'd like to address on this slide. It looks like this slide is blank or doesn't have any specific content to discuss. If there's anything you'd like me to explain, or if we've missed some details, please let me know. Otherwise, we can move on to the next slide. It looks like this slide is blank or doesn't contain any visible content for us to discuss. If there's specific information or key points you'd like me to elaborate on, please let me know so I can help you present them effectively. It looks like this slide is blank or missing content. Could you please provide the specific text or details you'd like me to narrate? That way, I can help you craft an effective presentation script. Now let's talk about pass transistor logic, or PTL families. These include several types like complementary pass transistor logic, swing restored pass transistor logic, double pass transistor logic, and differential cascode switch with pass gate logic. One of the main advantages of PTL families is their fast switching speed, which makes circuits more efficient. They also require fewer transistors, which reduces the overall capacitance in the circuit. This lower capacitance contributes to better performance and less power consumption. Another key point is that all Boolean functions can be implemented using these families, making them very versatile. Plus, the design process tends to be simpler compared to some other logic families. Overall, PTL families offer an effective combination of speed, simplicity, and flexibility. Here, we are designing a circuit to compute the function f equals AB plus CD, using only NAND and NOR gates. Initially, by inspection, we see that the circuit consists of two AND gates feeding into an OR gate, as shown in the first figure. Moving to the second figure, these AND OR gates are then translated into their corresponding basic CMOS stages. The next step involves simplifying the logic through a technique called bubble pushing, which you can see illustrated in the third and fourth figures. This process reduces the circuit to just 3 NAND gates, making it more efficient while still implementing the original function. This method highlights how careful manipulation of logic gates can streamline circuit design significantly. Now, let's talk about transmission gates, or TGs. The main reason we use transmission gates is to address the limitations of individual transistors. You see, an NMOS transistor is great at passing a strong zero, almost like a perfect switch for a low signal. However, it struggles when passing a high signal or a 1, making it weak in that case. On the other hand, a PMOS transistor works the opposite way. It passes a strong 1 but a weak 0. To solve this problem, transmission gates combine both types of transistors. A transmission gate is essentially a bidirectional switch formed by connecting a PMOS and an NMOS transistor in parallel, with their drain and source terminals shorted. This arrangement allows the gate to efficiently transmit the input signal in one state while blocking it in the other. The way we control this is by applying a control signal, which we call C, to the gate of the NMOS transistor. At the same time, the complementary signal, C', is sent to the gate of the PMOS transistor. This complementary control ensures that when one transistor is on, the other is off, enabling optimal signal transmission without distortion. This clever combination helps overcome the weaknesses of individual transistors, making transmission gates very useful in digital circuits. It seems this slide is blank without any specific content. Since there is no information provided here, I would suggest we move on to the next slide where we have details to discuss. If you have something specific you want to include or highlight on this slide, please let me know. Let's talk about transmission gate logic. When the control signal C is equal to 1, both the NMOS and PMOS transistors turn on, allowing the signal to pass freely between nodes A and B. In other words, A equals B when C is 1. However, when C is 0, both transistors turn off, effectively creating an open circuit between A and B. No signal passes through. On the discharging side, if node B is initially at VDD and node A is low, the PMOS transistor alone cannot pull node B down and turns off. Instead, the parallel NMOS transistor activates and pulls node B all the way down to ground, ensuring proper discharge. This interaction between the transistors is crucial for controlling signal flow in transmission gate logic circuits. It seems like this slide is currently empty and doesn't contain any content. If you'd like, you can provide me with the information or key points you want to include here, and I can help you craft a clear and engaging narration for it. It looks like this slide doesn't contain any text or visual elements for me to explain. Could you please provide the content or main points you want me to cover? That way, I can create a clear and engaging narration for you. Let's talk about the advantages first. One major benefit is that complex gates can be built using a minimal number of transistors, which helps reduce parasitic effects and improves overall efficiency. Additionally, by combining both PMOS and NMOS transistors in a transmission gate setup, we effectively avoid issues like reduced noise margins, increased switching resistance, and higher static power dissipation caused by threshold voltage increases. However, this arrangement does require that both the control signal and its complement are available to function properly. On the downside, time skew problems can cause short circuits, which is a significant risk to consider. Transmission gates also tend to operate at slower speeds compared to other options. Another limitation is related to charge sharing. You can't connect more than 3 transmission gates in cascade without running into problems. Beyond 3, a buffer circuit becomes necessary to maintain proper operation and signal integrity. Here, we're focusing on dynamic CMOS logic, which is a technique used in digital circuits to improve speed and reduce transistor count. Unlike static CMOS logic, dynamic logic uses a clock signal to control the evaluation of the output, enabling faster switching and smaller circuit sizes. It operates in 2 phases. The pre-charge phase, where the output node is set to a known state, and the evaluation phase, where the logic function is processed based on the inputs. This approach allows for quicker transitions, but requires careful timing to avoid errors. Overall, dynamic CMOS logic is a powerful method for designing high-performance integrated circuits. Here, we're looking at the drawbacks of ratioed circuits. One major issue is the slow rising transitions, which can limit the speed of the circuit. Then, there's contention during the falling transitions, causing conflicts that affect performance. Ratioed circuits also suffer from static power dissipation because of the continuous current flow. Additionally, the output voltage low level VOL is non-zero, meaning it doesn't fully reach ground, which can be problematic for logic levels. Dynamic circuits help to address these problems by using a clocked pull-up transistor instead of a PMOS transistor that's always on. This clocked approach controls when the transistor is active, reducing power consumption and improving transition speeds. The dynamic inverter shown here illustrates this concept, where the clock signal controls the pull-up device, enabling efficient operation and overcoming the limitations we see in ratioed circuits. This approach is crucial in designing faster and more power-efficient digital logic. Let's talk about how dynamic circuits operate, focusing on the 2 main modes, pre-charge and evaluation. During the pre-charge phase, the clock signal is at 0, which turns on the clocked PMOS transistor. This action sets the output, Y, to a high state, effectively preparing the circuit for the next step. Then, when the clock transitions to 1, we enter the evaluation mode. At this point, the clocked PMOS turns off, and the circuit looks to either keep the output high or discharge it to low through the pull-down network, depending on the input conditions. This 2-step process allows dynamic circuits to function efficiently, balancing speed and power consumption. Now let's look at the advantages and disadvantages of this design. On the positive side, it's the fastest option available, which means it can handle operations very quickly. It also has lower input capacitance, which helps improve performance since it requires less charge to change states. Another benefit is that there's no contention during switching, so the transitions are smooth and reliable. However, there are some downsides to consider. First, it requires careful clocking to ensure everything operates correctly, which can add complexity to the system design. It also consumes a significant amount of dynamic power, meaning it could be less energy efficient in certain applications. Lastly, this design is sensitive to noise during evaluation, so it's important to maintain a clean and stable environment to avoid errors. Overall, while it offers speed and efficiency, these trade-offs must be managed carefully. Here, we're looking at the concept of a dynamic gate, which operates using a 2-phase clock cycle, Precharge and evaluate. During the precharge phase, when the clock is at 0, the output node is charged to a known state. Then, during the evaluate phase, when the clock goes high, the circuit evaluates the logic function based on the inputs. In this example, the output implements the logic expression AB plus C. During evaluation, if either both A and B are high or C is high, the output will reflect that. The PMOS and NMOS transistors are controlled by the clock signals to either precharge or evaluate the node. This dynamic operation is efficient because it reduces power consumption by avoiding static current paths during certain phases. Understanding these phases and how the clock transitions control the transistor states is crucial for designing and analyzing dynamic logic circuits effectively. Let's talk about the conditions on the output in a dynamic gate. First, once the output has been discharged, it cannot be charged again until the next pre-charge operation occurs. This is an important behavior to keep in mind because it defines the timing and operation cycle of the gate. Next, the inputs to the gate are limited to making at most one transition during the evaluation phase. This restriction helps ensure stable and predictable operation. Lastly, the output can be in a high impedance state both during and after evaluation, which happens when the pull-down network is off. In this state, the output's value is effectively stored on the load capacitance, or CL. This characteristic is crucial because it allows the gate to hold a value even when it's not actively being driven. Let's dive into the properties of dynamic gates. First, the logic function in dynamic gates is implemented solely by the pull-down network, or PDN, which simplifies the design compared to static gates. Regarding transistor count, dynamic gates require N plus 2 transistors, whereas static complementary CMOS needs twice as many, or 2N, which means dynamic gates can be more efficient in terms of transistor usage. The outputs achieve full voltage swings, meaning the low output voltage hits ground level, and the high output voltage reaches the supply voltage, VDD, ensuring clear signal levels. Dynamic gates also benefit from faster switching speeds, making them suitable for high-performance applications. Another advantage is the reduced load capacitance. This happens due to lower input capacitance, referred to as CIN, and also because of smaller output loading, or COUT. Finally, there is no direct current path or short-circuit current. So all the current supplied by the PDN is effectively used to discharge the load capacitance, which increases power efficiency. Overall, these properties highlight why dynamic gates can be advantageous in specific design contexts. Let's delve into the properties of dynamic gates. First, it's important to note that overall power dissipation in dynamic gates is usually higher compared to static CMOS. This might seem counterintuitive at first, but it happens because dynamic gates don't have a static current path between VDD and ground, meaning there's no continuous current flowing when the gate is steady, which theoretically saves power. However, dynamic gates tend to have higher transition probabilities, leading to more frequent switching activity and an extra load on the clock signal, both of which contribute to increased power consumption. Another crucial point is that dynamic gates do not experience glitching. This is an advantage in terms of signal integrity and noise reduction during operation. On the downside, dynamic gates have a low noise margin, especially the low noise margin NML, which makes them more susceptible to disturbances and noise, potentially affecting reliability. In summary, while dynamic gates eliminate static current paths and prevent glitching, their higher switching activity and clock load lead to increased overall power dissipation, and the low noise margin remains a critical consideration in their design and implementation. Here we're discussing footed dynamic circuits, focusing on how to handle contention during the precharge phase. If input A is 1 during precharge, both the PMOS and NMOS transistors can turn on simultaneously, causing contention and potential circuit malfunction. To prevent this, when we can't guarantee that input A will be 0 during precharge, we introduce an extra clocked evaluation transistor at the bottom of the NMOS stack. This additional transistor is known as the foot. By adding the foot transistor, we effectively isolate the evaluation network during precharge, eliminating contention and improving circuit reliability. This concept is illustrated here with a footed dynamic inverter, where the foot transistor controls the connection to ground during different clock phases, ensuring proper operation. Here we're looking at the concept of generalized footed and unfooted dynamic gates. On the left side, we have the footed dynamic gates, which include the inputs labeled as F, Y, and F. The term footed refers to gates that have certain structural supports or constraints that influence their behavior. On the right side, we have the unfooted dynamic gates, again with the same input labels, F, Y, and F. The unfooted gates differ in that they lack those specific supports, which can affect their performance and response in different ways. Understanding these distinctions is crucial because the presence or absence of footing can fundamentally change how the gates operate dynamically under various conditions. This comparison sets the groundwork for deeper analysis of gate behaviors in dynamic systems. Here, we're looking at a key limitation of dynamic circuits called the monotonicity problem. Essentially, when a dynamic gate is evaluating, the inputs need to follow a specific pattern. They must be monotonically rising. That means the input signals can either start low and stay low, start low and then rise to high, or start high and remain high. However, the critical issue is that an input cannot start high and then fall back to low during evaluation. This constraint is important because violating it can cause incorrect operation or glitches in the circuit. So, understanding this monotonicity problem is essential when designing or working with dynamic circuits to ensure proper functionality. During the pre-charge phase, the output node is pulled high, preparing the circuit for the next evaluation. When the clock signal rises, the input is high, which causes the output to discharge low through the pull-down network or PDN. However, when the input later falls to low, the pre-charge transistor switches off, causing the output to float. This means the output remains low instead of rising, as one might expect. As a result, the output stays low until the next pre-charge cycle occurs. This behavior highlights what's known as the monotonicity problem, where the output doesn't transition smoothly in one direction during the evaluation phase. Understanding this issue is crucial for designing reliable dynamic logic circuits. Here, we're looking at some critical signal integrity issues that arise in dynamic design circuits. One major concern is charge leakage, which happens when the stored charge in the dynamic node gradually diminishes over time. This leakage primarily comes from subthreshold current, meaning current that flows even when the transistor is supposed to be off. This leakage can cause the output voltage, or Vout, to degrade, potentially leading to incorrect logic levels. To understand this better, consider the clock signals, labeled as CLK, which control the timing of the pre-charge and evaluate phases. During the pre-charge phase, the dynamic node is charged to a certain voltage level. Then, in the evaluate phase, this charge determines the output state. However, if charge leaks away before evaluation completes, the output may not reflect the intended logic. Additionally, various leakage sources, like transistor junction leakage and gate oxide leakage, contribute to this problem, but subthreshold leakage is often the dominant factor. This means managing leakage current is essential for maintaining signal integrity and ensuring reliable operation in dynamic circuits. Here, we focus on the solution to charge leakage in circuits. The main idea is to use a keeper to maintain the stored charge and prevent it from dissipating over time. This approach is similar to the level restorer technique used in past transistor logic. By implementing a keeper transistor, identified here as MKP, we can effectively counteract leakage currents, ensuring the node labeled out retains its value. The keeper works alongside other transistors, such as Mi and MP, to stabilize the output signal, while clock signals, CLK, control the timing of these actions. Overall, this method significantly improves the reliability of charge storage by maintaining signal integrity despite leakage paths. Now, let's discuss charge sharing. This occurs when the charge originally stored on the capacitor CL is redistributed between CL and another capacitor, CA. In this circuit, when the clock signals activate, the charge on CL doesn't stay fixed. Instead, it spreads out over both capacitors. This redistribution causes the voltage on CL to drop, which can reduce the robustness of the stored data. Essentially, because the charge is shared, the signal integrity weakens, making it more vulnerable to errors. This is a critical factor to consider in the design, as it directly impacts the reliability of the circuit's output. Here, we're looking at backgate coupling, which is an important concept to understand in circuit behavior. When the input signal goes from 0 to VDD, the output of the static NAND gate, labeled as out2, transitions from VDD down to 0. This change at out2 doesn't just stay isolated. It actually influences out1 due to capacitive coupling between the nodes. Specifically, out2 pulling down causes out1 to be pulled down as well, even though out1's driver is dynamic NAND. This effect occurs because the capacitive coupling between the backgate terminals transfers the voltage change, leading to unintended voltage shifts in connected nodes. Understanding this interaction is crucial when analyzing circuit stability and timing, especially in mixed dynamic and static logic gates. Here, we're focusing on the solution to charge redistribution, which is a common challenge. The key idea is to pre-charge internal nodes using a transistor controlled by a clock signal. This approach helps stabilize the charge distribution before the next operation, ensuring more reliable performance. However, it's important to note that implementing this clock-driven pre-charge transistor does come with trade-offs. It increases both the area required on the chip and the overall power consumption. Despite these costs, this technique is crucial for managing charge redistribution effectively in many circuit designs. Here, we are looking at the backgate coupling effect and its impact on signal timing. The graph shows time in nanoseconds along the horizontal axis, with several signals plotted. You can see the clock signal, the input signal, and two output signals, out1 and out2. The numbers along the vertical axis represent voltage levels, with values ranging from -1 up to 6. What stands out is how the coupling through the backgate can shift the output signals, affecting their timing and levels. This effect is critical to understand because it can influence circuit reliability and performance, especially at smaller technology nodes where coupling effects become more pronounced. By analyzing these timing differences, we can better design circuits to mitigate unwanted interactions and ensure stable operation. Here, we are focusing on clock feed-through, which is an important phenomenon in circuit design. Essentially, clock feed-through occurs because of the coupling between the output node and the clock input of the pre-charge device. This happens due to the gate-to-drain capacitance. What this means in practice is that the voltage at the output node can actually rise above the supply voltage, VDD, which is something we need to be aware of when analyzing the behavior of the circuit. The key point is that the fast transitions, the rising and falling edges of the clock signal, can couple into the output node, causing unwanted voltage spikes. Understanding this helps us design better circuits by minimizing these effects and ensuring more stable output signals. Now, let's look at some of the other effects that can impact our circuit performance. First, capacitive coupling between output wires can pull down the Prester charges, which can cause unintended signal variations. Then there's substrate coupling, where interference in the substrate can affect device behavior. We also have minority charge injection, which introduces extra charges that can alter the output. Finally, supply noise, especially negative ground bounce, can discharge the output unexpectedly. All of these factors are important because they can degrade the reliability and accuracy of our system if not properly managed. Here, we're looking at cascading dynamic gates, which are a bit different from static gates. The key point to remember is that only 0 to 1 transitions are allowed at the inputs of these gates. This is crucial because if we connect these gates directly without considering this limitation, it can lead to issues such as output signal loss. You'll notice multiple clock signals labeled CLK, which are essential for controlling the timing of these gates. The inputs labeled in, along with intermediate signals like M, P, and ME, are part of the internal operation, managing charge and ensuring the correct dynamic behavior. One important thing to understand is the concept of voltage change, represented here as delta V over time. This highlights how the signal voltage can degrade as it passes through the stages, which is why proper design is necessary to prevent signal loss and maintain performance. So, when working with cascading dynamic gates, always keep in mind the direction of signal transitions and the need to avoid direct connections that could compromise signal integrity. This careful handling ensures the dynamic gates function reliably within your circuit. Here, we're looking at the issue of incorrectly connecting dynamic gates that share the same clock signal. The key problem arises from what's known as the monotonicity problem. Essentially, when two dynamic gates are connected directly while using the same clock, it can cause timing and signal integrity issues. This happens because the output node might not maintain a stable voltage level during certain clock phases, which can lead to incorrect logic values being propagated. So, it's crucial to avoid these direct connections to ensure that the circuit functions reliably. The labels Y, A, X, and F on the diagram help us identify the relevant signals and nodes involved in this situation. Let's take a closer look at domino logic. This slide shows key components like the pull-down network, or PDN, and various inputs, such as in 1, in 2, and in 3. We also see important signals, including ME, MP, and the clock signals labeled CLK. The outputs are indicated as out 1 and out 2 for different sections. Notice how the circuit ensures timing synchronization with the clock signals controlling the logic flow. An essential point here is that the transitions between logic states are carefully managed. The notation shows how a 1 can remain 1, switch from 1 to 0, or how 0 maintains itself or changes to 1. This is crucial because we want to guarantee proper transitions from 0 to 1 between the gates, which helps avoid errors or glitches in the output. Essentially, domino logic relies heavily on these controlled transitions and clock timing to function correctly and efficiently in digital circuits. So why domino? The idea here is that the process works much like a chain reaction, similar to falling dominoes. Each step or element triggers the next one in sequence. We begin with initial triggers, followed by a series of clock signals, power delivery networks, and injection processes that interact systematically. This cascading effect ensures smooth operation and synchronization throughout the system. Just like dominoes tipping over one after another, each component's action initiates the next, creating a reliable and efficient progression. This metaphor helps us understand the interdependence and timing crucial to the entire mechanism. Now, let's discuss some important properties of domino logic. First, domino logic only allows the implementation of non-inverting logic functions. This is a key limitation to keep in mind when designing circuits. One of its major advantages is its very high speed, making it suitable for high-performance applications. The static inverter used in domino logic can be intentionally skewed, supporting only low to high transitions. To achieve this, the PMOS transistor in the inverter is made stronger. Additionally, domino logic benefits from reduced input capacitance, which translates into a smaller logical effort. This reduction in logical effort is important because it helps conserve power and improve overall circuit efficiency. Together, these properties make domino logic a powerful technique for fast and efficient digital circuit design. Here we're looking at designing with domino logic, which is a dynamic logic technique used to improve speed and reduce power consumption in digital circuits. The key components here include the PMOS transistors labeled MP, the NMOS transistors labeled ME, and the power supply VDD. Notice how the circuit is driven by the clock signal CLK, which controls the pre-charge and evaluation phases. During the pre-charge phase, indicated by the clock, the internal nodes are charged to a high voltage level. Importantly, the inputs in 1, in 2, and in 3, or in 4 in the second example, are 0 during this phase to prevent unwanted discharge. This 0 input state during pre-charge can be eliminated in some designs, but we must be cautious. Eliminating this constraint might introduce a short circuit path caused by a delayed clock signal, leading to potential timing hazards. So, while domino logic offers a powerful way to speed up computations, careful attention must be paid to clock timing and input controls to avoid these pitfalls. Here we're looking at the footless domino logic style. The key point is that the first gate in this domino chain requires a foot switch to avoid unwanted switching. However, within the chain, precharge causes a ripple effect, which leads to short-circuit current that can reduce efficiency. To address this, a practical solution is to delay the clock signal at each stage, ensuring that the transitions happen sequentially rather than simultaneously. This stage clocking helps to minimize the short-circuit current and improve overall circuit performance. The diagram illustrates the typical connections, with each stage receiving its own delayed clock signal, and the inputs and outputs cascading through the chain. Understanding this mechanism is crucial for optimizing dynamic logic circuits. Now let's talk about various types of domino logic and some key optimizations we can apply to domino logic gates. First, we have the dual-rail differential domino logic gate, which helps improve noise immunity and logic robustness by using complementary signals. Then, there's the multiple output domino, which optimizes performance by generating more than one output from a single domino stage, effectively enhancing circuit efficiency. Lastly, NP-CMOS domino logic integrates both N-type and P-type transistors to achieve better speed and power efficiency. These optimizations are crucial for enhancing the overall performance and reliability of domino logic circuits. Here, we're looking at the differential or dual-rail domino logic. This technique addresses the challenge of implementing non-inverting logic efficiently. On the slide, you can see the use of two inputs labeled A and B, along with their complements, not A and not B, which are essential for differential operation. The key transistors Mi and MP work together with their counterparts MKP and MKP to control the logic evaluation. The clock signals shown synchronize the circuit's operation, ensuring the correct timing for evaluating the logic function. Notice that the output, shown as out equals AB, signifies the function of inputs A and B, maintaining a non-inverted output. With the dual-rail approach, the circuit effectively prevents errors commonly encountered in standard domino logic by using complementary signals. This design improves robustness and reliability, which is critical in high-performance digital circuits. Overall, the differential domino logic combines speed and correctness by leveraging complementary inputs and careful clocking, solving the problem of non-inverting logic in dynamic circuits. Here, we're focusing on multiple output domino logic. This technique allows us to drive several outputs from a single dynamic node, enabling more compact and efficient circuit designs. The key advantage is that it reduces the number of dynamic nodes needed, which can save power and area. However, managing multiple outputs requires careful timing and signal integrity considerations to ensure reliable operation. Understanding how to implement and optimize multiple output domino logic is crucial for improving overall circuit performance. Here we're looking at the NP-CMOS structure and focusing on the switching behavior of the pull-down network, or PDN, and the pull-up network, or PUN. It's important to note that only certain transitions are allowed at their inputs. For the PDN, the inputs can only switch from 0 to 1, while for the PUN, the inputs can only go from 1 to 0. This helps to maintain proper operation and avoid conflicts. In the diagram, you can see the inputs labeled for both networks, with the PDN inputs going into transistors connected to ground, and the PUN inputs controlling transistors connected to the power supply. The clock signals manage these switches, ensuring the right timing. One key point here is that the allowed transitions help prevent short circuits during switching phases, since both networks are never turned on simultaneously. However, we need to be mindful of possible coupling effects in longer transistor runs, especially at the dynamic node. This can potentially lead to unintended charge sharing or noise, which might impact circuit reliability. So, understanding these allowed input transitions and their implications on the PDN and PUN helps us design more robust and efficient CMOS circuits. Dual-rail logic circuits are also known as differential logic because they process both the true signal and its complement simultaneously. This approach helps improve noise margins and speed. There are several main types of dual-rail logic circuits that are commonly used. These include cascode voltage switch logic, which is known for its high-speed switching, complementary pass transistor logic, which is efficient in terms of transistor count, double pass transistor logic, offering reduced power consumption, and differential cascode voltage switch with pass gate logic, which combines the benefits of differential operation and pass gate control. Each of these types offers unique advantages depending on the specific application. Here, we're focusing on the complementary pass transistor, commonly abbreviated as CPL. This is a key concept in transistor logic design, where two transistors, one N-type and one P-type, work together to pass a signal more efficiently. By combining both types, CPL circuits can achieve faster switching speeds and improve power efficiency compared to traditional approaches. This makes CPL a valuable technique in optimizing digital circuits, especially in low-power and high-performance applications. Understanding how the complementary transistors interact is crucial for mastering modern transistor logic design. Now let's talk about the drawback of the CVSL or cross-coupled voltage sense logic. While CVSL employs a PMOS cross-coupled latch as its load, it faces a significant limitation. The PMOS latch is regenerative, meaning it tends to maintain its state, which makes it difficult to invert quickly. This property slows down the operation, so the CVSL can't achieve the high speed we might expect. However, this issue can be addressed by using complementary pass transistor logic, or CPL, which offers a way to overcome this speed limitation effectively. Complementary pass transistor logic, or CPL, is a design style for implementing logic gates that primarily uses NMOS-only pass transistor networks. Each gate is followed by a CMOS output inverter, which means that the traditional PMOS cross-coupled latch is no longer necessary. What's important here is that CPL uses complementary inputs and outputs, along with two NMOS networks that realize both a function and its complement, F and F bar. These two NMOS networks act as pull-up and pull-down devices, effectively replacing the role of the PMOS latch. This configuration allows for more efficient gate designs by simplifying the circuit and potentially improving performance. Here, we're discussing the role of output buffers in compensating for voltage threshold losses caused by pass transistors. Essentially, these buffers help restore the signals back to their correct voltage levels, ensuring reliable circuit operation. Additionally, a PMOS latch can be introduced in the CPL, which helps cut down on static power dissipation. This specifically addresses situations where the output buffer sees a high-level input voltage that isn't fully high. It's important to note that when a CPL circuit functions as an intermediate logic stage, we can sometimes omit these output buffers altogether. Moving on, the CPL function networks are typically implemented using the 0/1 x/x bar tree network paradigm, but with a small adjustment. The constants 1 and 0 at the dual rail inputs aren't fixed. They need to be replaced by variables following certain switching algebra properties. This substitution is crucial to ensure that the resulting logic circuit can be cascaded properly without issues. So, understanding these algebraic properties and how they impact network realization is key when working with CPL circuits. Here, we're looking at an example of a two-input CPL and /NAND gate using CPL style. The focus is on NAND logic. Starting from the block diagram of CPL, the function for the NAND gate is represented as f prime equals the complement of x and y, or f prime equals the complement of x dot y. Then, this expression is expanded with respect to y, transforming into f prime equal to x complement y. This can be rewritten as x complement plus y complement, which is equivalent to y prime plus y double prime times x prime. Next, we apply further steps. F prime equals y complement multiplied by 1 plus y multiplied by x complement. This is simplified to y complement times y complement plus y times x complement. Lastly, we invoke De Morgan's law, which states that a plus b equals a plus a complement times b. This helps us understand the transformation and simplification in the NAND logic expression. The key takeaway is how CPL style uses these Boolean algebra expansions and laws to derive the logic function for the NAND gate. Here, we're looking at the function for a two-input and gate, represented as f equals x and y, or simply xy. To analyze this, we expand the function with respect to one of the variables, in this case, y. The idea is to express f in terms of y and its complement. We start by writing f as xy, then rewrite it as y times x plus y complement times 0. Since when y is 0, the function output is 0 regardless of x. This leads us to the expression f equals y complement times 0 plus y times x, simplifying to f equals y times x because the first term drops out. This approach helps to break down complex functions by focusing on one variable at a time, making it easier to understand and manipulate in logic circuit design. Here, we're looking at XOR and XNOR gates. The XOR gate outputs true only when the inputs are different. Its function can be expressed as f equals x XOR y, which breaks down into the sum of two terms, not y and x, plus y and not x. In other words, it outputs true when either x or y is true, but not both. On the other hand, the XNOR gate is essentially the complement of the XOR. Its output is true when the inputs are the same. Its function f complement is the sum of not y and not x plus y and x. Understanding these gates is essential, as they form the basis of many digital logic operations where differentiation or equality between signals is required. Double pass transistor logic, or DPL, is essentially a modified version of complementary pass transistor logic, designed specifically for lower supply voltage environments. Unlike CPL, which typically uses mainly NMOS transistors, DPL incorporates both NMOS and PMOS switches to achieve its logic functions. This approach helps it operate more effectively when voltages are reduced. Similar to CPL, DPL gates feature both true and complementary inputs and outputs, making them dual-rail logic circuits. One of the important characteristics of DPL is that it maintains balanced input capacitance. This means every input connects symmetrically to the same number of transistor gates and sources. This balance is crucial because it helps in reducing glitches and improves signal integrity by ensuring consistent load on all inputs. Overall, these features make DPL well suited for applications where power efficiency and reliable operation at low voltages are key. Here, we see that this design achieves a balanced input capacitance, which is crucial because it helps minimize how much the propagation delay depends on the data pattern being processed. Essentially, the delay remains more consistent regardless of the input values, which improves overall performance. Another important feature is the double transmission characteristic. This happens because both NMOS and PMOS transistors are used in the circuit. This dual transistor approach means the circuit doesn't require output buffers to restore voltage levels, unlike the conventional CPL logic style. To illustrate this, let's consider the example of a two-input DPL AND gate. Using Shannon's expansion theorem, the switching function for the AND gate, which is f equals x and y, can be expanded with respect to both input variables x and y. The expression shows how the function can be broken down and analyzed in terms of simpler components based on the inputs and their complements. This approach helps in designing the logic and understanding its operation in deeper detail. Here, we are looking at the switching function of a two-input NAND gate, which is represented as f prime equals the complement of x and y. This function can be expanded considering both variables x and y. The equation shows that f equals the complement of x or the complement of y. Then it's further broken down into two parts, one involving x and its complement combined with y complement, and the other involving y and its complement combined with x complement. Notice that we apply the rule where the complement of x times 1 equals the complement of x times itself. This helps simplify the expression and makes the logic behind the NAND gate more clear. Understanding this expansion is key to analyzing and designing digital circuits effectively. It looks like this slide is blank or missing content. Could you please provide the text or main points you want me to cover for this slide? That way, I can create an effective narration for you. One of the main drawbacks of differential pair logic, or DPL, is that it isn't straightforward to directly implement any arbitrary switching function with it. For more complex functions, like a full adder, The design typically involves combining several basic logic gates implemented in DPL. This approach often creates a long chain of MOS transistors. The longer this chain, the longer the propagation delay for the input signal to travel through from the transistor chain to the output. Such delays can be significant enough to cause problems in applications where speed and timing are critical. So, while DPL has its advantages, this potential for increased delay is an important consideration. Here, we're looking at the differential cascode voltage switch with pass-gate logic, or DCVSBG for short. This logic style essentially merges two well-known designs, the CVSL and the CPL. Specifically, it takes the output stage from the CVSL design and combines it with a logic network style of CPL to create the desired logic functions. One important point to note is that unlike CPL, the DCVSBG circuit is usually a standalone design. It's not typically intended to be cascaded or chained together, which sets it apart from CPL in how it's used. Because of this standalone nature, the logic functions in DCVSBG can be directly designed using the 0/1 x/x bar tree network model, which simplifies the design process quite a bit. This combination allows DCVSBG to offer a unique blend of features from both CVSL and CPL, making it a versatile approach in certain logic circuit applications. It seems this slide doesn't contain any content for us to discuss. If you have any notes or specific points you'd like me to cover here, please let me know, and I'll be happy to explain them thoroughly. It looks like this slide is currently blank or doesn't have any content to discuss. If you'd like, we can move on to the next slide, or I can help you add some key points here. Just let me know how you'd like to proceed. Here, we're looking at the function networks for a 2-input and /NAND gate. For the NAND gate, the function is expressed as f bar equals x and y, which can be expanded by focusing on the variable x. This expansion shows us that f bar equals the complement of x plus the complement of y, or in another form, it can be written as the complement of x times 1 plus x times the complement of y. On the other hand, for the AND gate, the function f equals x and y, and when we expand it with respect to x, it becomes the complement of x times 0 plus x times y. This shows how the function behaves depending on the value of x. Understanding these expansions helps in analyzing and designing logic circuits more effectively by breaking down the functions into simpler components. Now, let's take a closer look at common circuit pitfalls that can lead to chip failures. These issues are critical to understand when designing reliable electronics. First, threshold drops occur when the transistor's switching threshold shifts, which can cause improper operation. Ratio failures happen when the sizes of transistors in a circuit are not balanced correctly, leading to functional errors. Leakage refers to unwanted current flow that causes power loss and potential malfunction. Charge sharing is a tricky phenomenon where charge moves between nodes unexpectedly, disrupting signals. Power supply noise is also a major culprit, as fluctuations can interfere with circuit stability. Coupling, where signals unintentionally influence each other, introduces errors as well. Going further, minority carrier injection can affect transistor switching behavior, and backgate coupling impacts the transistor's threshold by interaction with underlying substrates. Diffusion input noise sensitivity makes circuits vulnerable to subtle disturbances. Race conditions arise when timing issues cause unpredictable results, and delay matching problems lead to synchronization failures. Metastability is a state of uncertainty that can corrupt data, while hotspots refer to localized overheating that threaten circuit integrity. Soft errors caused by environmental factors like radiation can flip bits and disrupt functionality. Lastly, process sensitivity highlights the variations in manufacturing that impact circuit performance. Being aware of these pitfalls is essential for robust chip design. Here, we're talking about threshold drops in pass transistors. Pass transistors work well when pulling a signal in their preferred direction, meaning they can effectively pass a strong logic level. However, when the signal tries to swing in the opposite direction, it can only do so up to within the transistor's threshold voltage of the supply rail. This limitation is what we refer to as a threshold drop. Essentially, it means the output voltage won't fully reach the rail voltage, which can affect the performance in certain circuits. Understanding this behavior is crucial when designing reliable transistor-based logic circuits. Here we see a pass transistor driving a logic high, or a logic 1, into an inverter. The key point is that the output voltage of the pass transistor only rises up to VDD minus the threshold voltage, VT. This happens because of the body effect, which increases the threshold voltage when the source-to-body voltage, VSB, is 0 for the pass transistor. This degraded voltage level isn't high enough to fully switch off the PMOS transistor in the inverter. As a consequence, the PMOS transistor never completely turns off, leading to static power dissipation, which we want to avoid. To fix this issue, pass transistors are often replaced with full transmission gates. Alternatively, weak PMOS feedback transistors can be added to pull the output voltage all the way up to VDD. This approach was previously used in several pass transistor logic families to eliminate the problem and reduce static power consumption. Here we're looking at ratio failures, which commonly happen in pseudo-NMOS circuits. These failures arise due to ratio constraints, basically situations where a node is being pulled up and down at the same time. This usually involves strong NMOS transistors pulling down, while weak PMOS transistors try to pull up. The key is that these weak PMOS transistors need to be small enough so the output voltage drops below the VL threshold of the following stage, ensuring proper logic interpretation and some noise margin. Ideally, we want the output to fall below the transistor threshold voltage, VT, so the next stage doesn't end up using static power unnecessarily. Ratio failures can also show up in circuits that incorporate feedback, which makes managing these constraints even more critical. It looks like this slide doesn't have any content yet. If you provide the details or key points you'd like to cover, I can help you create a clear and engaging narration for it. Ratioing is particularly critical when dealing with diffusion inputs. To illustrate, in Figure A, we have a static latch that includes a weak feedback inverter. The feedback inverter has to be intentionally weak so that it can be overridden by the combined effect of the pass transistor along with the gate that drives the D input, which you can see in Figure B. It's important to note that this setup can't be properly verified just by examining the latch on its own. We need to perform a global analysis that takes into account both the latch and the driver together. Additionally, if the driver is located at a significant distance, we need to factor in the resistance of the series wire as well, as demonstrated in Figure C. This ensures the signal integrity is maintained throughout the circuit. Leakage current is becoming an increasingly significant issue as technology continues to scale down, particularly affecting dynamic nodes and wide NOR structures. This leakage mainly stems from three sources: subthreshold conduction, gate tunneling, and reverse bias diode leakage. Among these, subthreshold conduction is currently the biggest contributor because threshold voltages are low and getting even lower. However, gate tunneling is expected to become critically important as the oxide thickness decreases further. Besides causing static power dissipation, leakage can also lead to incorrect values on dynamic or weakly driven nodes. Essentially, the leakage current can disturb the voltage on these nodes over time, which raises concerns for reliable circuit operation. Here we're looking at the concept of charge sharing, which is an important phenomenon in dynamic circuits. Charge sharing can happen when dynamic gates drive past transistors. To illustrate, imagine a dynamic inverter connected to a transmission gate. Initially, the dynamic gate is precharged so that the output node is floating high, meaning it holds a positive charge. At the same time, the transmission gate is off, and the node Y is at 0 volts. Now, when the transmission gate switches on, the charge stored at the output node will redistribute between nodes X and Y. This sharing of charge causes the voltage at the dynamic output node to drop, which disturbs the expected logic level. Understanding this effect is crucial because it can lead to incorrect logic operation if not properly managed in circuit design. Power supply noise is an important factor to consider in chip design because both VDD and GND lines are not perfectly constant across a large chip. One major source of this noise comes from IR drops. These drops happen because of the resistance in the power supply grid. As current flows through this resistance from the supply pins to different blocks, voltage drops occur, causing fluctuations in the power supply. Another critical source of noise is D/DT noise, which is related to the inductance in the power supply network. When current changes rapidly, this inductance causes voltage spikes or dips. This effect is particularly notable in blocks that remain idle for several cycles and then suddenly switch on, leading to sharp current changes. Together, these factors contribute to power supply noise, impacting the stable operation of the chip. Let's talk about hot spots in transistors. As temperature increases, transistor performance decreases, so it's important to prevent areas on the chip from getting too hot. These hot spots often occur because power dissipation isn't uniform, even if the total power consumption is within limits. This uneven temperature distribution can cause differences in delay times between gates, which affects the overall reliability and performance of the chip. Managing these hotspots is crucial to maintain consistent operation and prolong device lifespan. Sometimes, a signal can briefly go beyond its normal voltage limits, either because of capacitive coupling or inductive ringing on the input-output drivers. When this happens, the junctions between the drain and the body of a transistor can become forward biased for a short time. This allows current to flow into the substrate, a phenomenon we call minority carrier injection. This effect is important to understand because it can impact the behavior and reliability of the device during operation. Here, we're looking at a situation where the drain of an NMOS transistor is driven below ground level. When this happens, electrons get injected into the P-type substrate. And these electrons don't just disappear, they can be collected on a nearby transistor's diffusion node. This collection of electrons can then disturb the voltage at that node, especially if it's a high voltage. This effect is particularly problematic for dynamic nodes, which rely on stable charge, and for sensitive analog circuits, where even small voltage disturbances can impact performance significantly. Understanding this helps us see why controlling substrate injection is critical in certain circuit designs. When dealing with minority carrier injection issues, it's important to keep injection sources away from sensitive nodes to prevent interference. A good example is ensuring that I/O pads are not placed too close to these sensitive nodes. To help identify areas where coupling might be a problem, noise analysis tools can be used. Once potential issues are found, the layout can be adjusted to minimize this coupling. Another effective approach is to protect the sensitive node by introducing an intermediate substrate or well contact, which acts as a barrier. For instance, in the example shown, most of the injected electrons are captured by the substrate contact before they can affect the dynamic node. Additionally, it's common practice to surround output transistors in I/O pads with guard rings made of substrate or well contacts. These guard rings help further isolate the transistors and reduce noise coupling. Here, we're looking at the phenomenon called backgate coupling, which occurs when dynamic gates drive multiple input static CMOS gates. In this example, we have a dynamic NAND gate driving a static NAND gate. Notice the gate-to-source capacitance, labeled CGS1, of transistor N1. Imagine the dynamic gate is in the evaluation phase, and its output, X, is floating high. At the same time, the other input, B, to the static NAND gate starts off low. Because of this, the output Y of the NAND gate remains high, and the internal node W becomes charged up to VDD minus the threshold voltage, VT. This setup is critical because any changes can influence the voltage at node W through backgate coupling, impacting the overall circuit behavior. Here, we're discussing diffusion input noise sensitivity in a static latch. The figure illustrates a static latch with the diffusion input exposed, which makes it particularly vulnerable to noise. Imagine power supply noise or coupling noise causing the input voltage to drop below the threshold voltage, relative to ground, at the transmission gate. When this happens, the gate-to-source voltage of the NMOS transistor exceeds its threshold, turning the transmission gate on unexpectedly. If the latch was holding a logic 1, This noise-induced turn-on could cause it to be erroneously discharged to zero. A similar problem arises if the voltage spikes above the supply voltage, VDD, potentially causing incorrect behavior. This highlights why controlling noise on diffusion inputs is crucial for latch reliability. When we talk about process sensitivity, we're referring to how certain circuits behave under variations in manufacturing conditions. Marginal circuits might work fine under standard nominal process conditions, but they can fail when exposed to specific process corners or if they're shifted to a different fabrication process. This is why novel circuits need thorough testing across all process corners. It's not enough to check their performance at just one set of conditions. We must simulate and analyze them under a wide range of scenarios. Additionally, we need to ensure these circuits function properly across all voltages and temperatures. This includes the higher voltages and temperatures used during burn-in testing, as well as the lower voltages that might be implemented for low-power versions. This comprehensive verification helps prevent failures and ensures robust circuit performance in real-world applications. Domino logic is quite sensitive to noise, so it requires careful verification to ensure correct operation. Unlike static CMOS gates, where noise typically just causes increased delay, in domino logic noise can actually lead to incorrect results, which makes managing it crucial. There are several noise sources we need to consider here. First is charge leakage, where stored charge can dissipate over time. Then there's charge sharing, which involves unwanted redistribution of charge between nodes. Capacitive coupling is another factor, where interference occurs due to capacitors coupling signals between adjacent lines. Lastly, backgate coupling can induce noise through the substrate or well. Understanding and budgeting for these noise sources helps us design more reliable domino circuits. Here, we're focusing on several important factors that can impact the performance and reliability of circuits involving minority carrier injection. First, power supply noise is a significant concern. To reduce this noise, it's crucial to place static gates close to the dynamic gates they control. This proximity helps minimize the interference caused by fluctuations in the power supply. Next, we have soft errors, which are random, non-destructive faults often caused by external radiation or electrical noise. Understanding and mitigating these errors is important for system stability. Noise feed-through is another consideration. It occurs when unwanted signals couple into sensitive parts of the circuit, potentially causing incorrect behavior. Lastly, process corner effects refer to variations in manufacturing that can affect device performance. These variations can cause changes in speed, power consumption, and reliability, so it's essential to account for them during design. Overall, managing these factors effectively helps ensure robust and reliable circuit operation. Here, we focus on power dissipation, which is a crucial concept when dealing with electronic components and circuits. Power dissipation refers to the process by which an electronic device converts electrical energy into heat. This happens because as current flows through a component, some energy is lost due to resistance or other factors, resulting in heat generation. Managing this heat is essential to ensure the device operates efficiently and avoids damage. Understanding power dissipation helps us design better cooling solutions and choose components that can handle the thermal load safely. Let's talk about power dissipation in static CMOS gates. One of the main advantages of these gates is their power efficiency, especially when they are idle. They consume almost no power during these periods. Now, when we discuss power, we often consider instantaneous power, which is the power at any given moment. Energy consumed over a period of time is crucial to understanding overall power usage. Average power is calculated by integrating the current drawn by the device multiplied by the supply voltage over a time interval, then dividing by the total time duration. Essentially, this average power gives us a practical measure of power consumption over the operating period, giving insight into how efficiently the circuit uses energy overall. Now, let's talk about power dissipation in CMOS circuits, which is a critical factor in designing efficient devices. Power dissipation here comes from three main components. First, we have static dissipation, which occurs even when the circuit is not switching. This includes subthreshold conduction, tunneling currents, and leakage through reverse bias diodes. Next, we have dynamic dissipation, which happens due to the charging and discharging of load capacitances during switching activities. Lastly, there's short-circuit power dissipation, which occurs because, for a brief time during switching, both the PMOS and NMOS transistors are partially on, allowing current to flow directly from the supply to ground. The total power dissipation is simply the sum of these three components: static, dynamic, and short-circuit power. Understanding and minimizing each of these components is key to optimizing CMOS circuit performance and energy efficiency. Here, we're focusing on static dissipation, which refers to the power consumed when a transistor is in the off state. The key formula for static power dissipation is the product of the supply voltage VDD and the static current is static. This power loss arises due to several non-ideal effects in the transistor's behavior. These include subthreshold conduction, where current leaks even below the threshold voltage, tunneling currents that occur at very small scales, and leakage through reverse bias diodes within the circuit. Additionally, in ratioed logic circuits, contention current can contribute to static power loss. Ideally, there should be no power dissipated when the transistor is off, but these non-idealities make some level of leakage inevitable. Understanding these leakage paths is crucial for designing low-power circuits. Here, we're looking at dynamic dissipation, which happens because of the continuous charging and discharging of a load capacitor. The load capacitance is represented by C, and the switching frequency is denoted as FSW. Within a given time interval T, the capacitor charges T times the switching frequency, meaning T multiplied by FSW. When the capacitor charges, current flows from the power supply, VDD, to the load. Then, during discharging, current flows back from the load to ground. In one full cycle of charging and discharging, a charge equal to C times VDD is transferred from the load to ground. This recurring transfer of charge is what leads to dynamic dissipation in the circuit. Understanding this helps us grasp how switching activity impacts power consumption. Let's talk about dynamic dissipation in digital circuits. This refers to the power consumed when a logic gate charges and discharges its load capacitance during switching. The integral expression here shows the relationship between the current flowing through the supply and the voltage over a period T. Essentially, the dynamic power can be calculated as the average current times the supply voltage. Assuming a logic gate switches once every clock cycle, the dynamic power dissipation is proportional to the capacitance, the square of the supply voltage, and the clock frequency. This is shown as P dynamic equals C times V square times F. However, since not every gate switches every cycle, we include an activity factor, alpha, which represents the fraction of time the gate actually switches. So the corrected formula becomes dynamic power equals alpha times capacitance times voltage squared times frequency. Understanding this helps us focus on reducing switching activity, voltage, and capacitance to lower power consumption in digital circuits. Here, we're looking at short-circuit power dissipation, which happens when both the pull-up network and pull-down network conduct at the same time during a brief transition period. This simultaneous conduction causes current to flow directly from the power supply to ground, resulting in power loss. The equation for short-circuit power dissipation is given by short equals Isher.T times VDD, where Isher.T is the short-circuit current and VDD is the supply voltage. It's important to understand that the total power dissipation in a circuit is the sum of three components: static power, dynamic power, and this short-circuit power. Each plays a crucial role in the overall energy consumption of the device. Now, let's dive into the key principles behind low-power design, starting with dynamic power reduction. Dynamic power is governed by a simple but powerful equation. Power equals the activity factor multiplied by capacitance, voltage squared, and frequency. Each of these components offers a lever to reduce power consumption. First, we can decrease the activity factor, which means reducing how often the circuit switch states. Next, reducing the switching capacitance by optimizing the circuit layout or using smaller transistors helps limit power usage. Lowering the power supply voltage has a significant impact because power scales with the square of the voltage. Finally, reducing the operating frequency, or how fast the circuit runs, also lowers dynamic power. By strategically addressing these factors, we can achieve efficient low-power designs without sacrificing performance. Now, let's look at dynamic power reduction techniques. One effective way is to decrease the activity factor, which means reducing how often parts of the circuit switch states. For example, using static logic or selective clock gating can help by stopping sections of the chip that aren't in use. However, there's a trade-off. If the system quickly switches from idle to fully active, it can cause a large current spike, which we need to manage carefully. Another approach is to decrease switching capacitance. This can be done by using smaller transistors and thoughtful floor planning, placing communicating devices close together to minimize interconnect capacitance. Reducing the power supply voltage VDD also has a big impact since power dissipation scales quadratically with voltage. Lowering VDD effectively cuts power consumption significantly. Finally, we can decrease the operating frequency. For instance, instead of running a single multiplier at a high speed, we can use two multipliers running at a lower speed, which helps reduce dynamic power overall. These strategies combined contribute significantly to managing dynamic power in a system. Here, we're focusing on strategies to reduce static power consumption. Static current, which contributes to power loss even when the circuit is idle, can be minimized by turning off analog sources and pseudo-NMOS gates when they're not in use. This approach helps prevent unnecessary current flow. Additionally, subthreshold leakage, which is another form of power loss, can be reduced by adjusting certain parameters. Increasing the threshold voltage, or VDO, helps block unwanted current. Lowering the drain source voltage, VDS, and increasing the source bulk voltage, VSB, also contribute to reducing leakage. Lastly, keeping the temperature down is crucial since higher temperatures exacerbate leakage currents. By managing these factors, we can effectively cut down static power consumption in our designs. Now let's talk about how we can control leakage using the body effect. This technique is crucial in managing power consumption in semiconductor devices. For low threshold voltage devices, we often apply reverse body bias or RBB, which helps reduce leakage current by increasing the threshold voltage. On the other hand, for high threshold voltage devices, forward body bias or FBB is used. This lowers the threshold voltage to improve performance when needed. There's also adaptive body bias or ABB, which dynamically adjusts the body bias based on operating conditions. This adaptability allows us to optimize both leakage and performance effectively. Understanding these biasing techniques is key to balancing power efficiency and device speed. Here, we're looking at MOS technology. The key idea is that MOS circuits use two types of transistors to manage power effectively. Low threshold voltage, or low VT, transistors handle the actual computation because they switch quickly and efficiently. Meanwhile, high threshold voltage, or high VT, transistors act as switches that can disconnect the power supply when the circuit is idle. This approach helps reduce leakage power without compromising performance during active operation. Essentially, MOS balances speed and power savings by smartly controlling the power flow based on activity. When we talk about low-power architectures, it's important to understand how the focus in VLSI design has shifted over time. In the past, the main limitation was how many transistors could physically fit on a chip. Designers aimed to get the maximum speed out of each transistor to boost overall performance. However, today, with billions of tiny transistors packed onto a single chip, the main challenge isn't just fitting them in, but managing power consumption. Now, energy efficiency has become the key to achieving high performance. The best designs are those that balance power use with speed. To accomplish this, energy-efficient architectures rely on design principles like modularity and locality. These principles help organize the processor in a structured way, reducing unnecessary energy waste. One interesting point is that processor performance tends to grow with the square root of a number of transistors, which shows that simply adding more transistors doesn't linearly increase performance. Instead, smart architectural choices are crucial to optimize energy use and get the best performance possible. Microarchitectures are evolving by incorporating more cores, but these cores are becoming simpler. The goal here is to better manage task and data level parallelism, allowing multiple processes to run efficiently at the same time. One advantage of smaller cores is that they benefit from shorter wiring and quicker memory access, which helps speed things up overall. Additionally, using special-purpose functional units can greatly improve energy efficiency, often by an order of magnitude, compared to general-purpose processors. This means we can achieve much better performance while consuming less power by tailoring hardware to specific tasks. To address the performance loss caused by lowering the supply voltage while keeping the threshold voltage unchanged, we rely on two key techniques: pipelining and parallel processing. Both methods aim to boost the system's concurrency, which directly enhances performance. Starting with parallel processing, this approach involves using multiple copies of the same circuit to perform computations simultaneously on different datasets. By doing so, we not only increase throughput, but also have the flexibility to reduce the supply voltage, which helps in lowering overall power dissipation without sacrificing performance. This balance between power and efficiency is crucial in modern system design. Here, we're looking at an M-parallel system, which means we have M identical copies of the function units working simultaneously. Because of this duplication, the total capacitance increases by a factor of M, since each unit contributes to the overall capacitance. Now, to keep the performance consistent despite this increased capacitance, we reduce the clock frequency by that same factor of M. This adjustment balances out the system's timing. When we take into account the capacitances of these parallel processing registers, the overall power dissipation in this M-parallel setup can be expressed in a specific way, reflecting both the increased capacitance and the reduced frequency. This relationship is crucial for understanding how parallel designs impact power consumption and helps guide low-power design strategies. Here, we're looking at how extending the charging and discharging time of the capacitors allows us to reduce the supply voltage by a factor of alpha. In the M-parallel system, the power consumption is expressed with this adjusted voltage, showing that by increasing parallelism, we can decrease power proportionally. Moving on to pipelining, it's a technique where data flows continuously through a circuit in a steady, ordered fashion, which lets us generate results in sequence without interruption. Importantly, pipelining helps save power because it permits us to lower the supply voltage while maintaining performance. So, both these methods, parallelism and pipelining, play a key role in reducing power consumption effectively. It seems like this slide is blank or doesn't have any content to present. If there's a specific point or idea you want to discuss here, please let me know, and I can help craft the narration accordingly. Otherwise, we can move on to the next slide. Power management spans across multiple levels, starting from the circuit and logic level, all the way up to the architecture, software, and system level. This holistic approach is crucial for optimizing power consumption effectively. Take the Intel Atom processor as an example. It normally runs at a peak frequency of 2 GHz with a voltage of 1 volt, consuming about 2 watts of power. However, when operating in low-frequency mode, the processor reduces its clock speed down to 600 MHz, and the power supply voltage decreases to 0.75 volts. This significant reduction in both frequency and voltage allows the processor to save power and operate more efficiently during less demanding tasks. Since this slide appears to be blank or contains no content, I'll take a moment to reflect on everything we've covered so far. We've explored the essential concepts thoroughly, and I hope the information shared has been clear and useful. If you have any questions or need further clarification on any point, now would be a great time to address them. Otherwise, thank you for your attention and engagement throughout this presentation. Thank you all for your attention and participation throughout this presentation. If you have any questions or need further clarification, please feel free to ask. It's been a pleasure sharing this information with you.